Hello there, and welcome to Science for Sleep, a place where curiosity slows its breathing, where questions are allowed to wander without needing quick answers, and where science is invited not to impress or overwhelm, but to gently accompany you toward rest. Wherever you are listening from tonight, whether the room around you is bright or dim, busy or quiet, I'm glad you're here. This channel exists for moments like this, when the mind is still awake enough to wonder, but ready to loosen its grip on the day. Tonight, we're going to spend some time with a question that sounds enormous at first, but unfolds very gradually when you sit with it. It's about size. Not the everyday kind, not the kind you measure with a ruler or estimate by eye, but cosmic size. The kind that doesn't fit neatly into intuition, the kind that stretches language a little thin. Recently, a new instrument has given us a clearer look than ever before, and what it revealed wasn't just more detail or prettier pictures or sharper data points. It quietly suggested that the universe may be larger, more extended, and more populated than we were fully prepared for. Not in a dramatic, headline-grabbing way, but in a slow, accumulative sense, where each observation gently nudges the scale outward. The James Webb Space Telescope didn't announce this with fireworks. It didn't flash a sign saying everything we knew was wrong. Instead, it did what careful science often does. It observed patiently. It gathered light that had been travelling for unimaginable lengths of time. It looked deeper into space, which also means earlier into time than any instrument before it designed to work this way. And in doing so, it showed us structures, patterns, and objects existing where, according to previous expectations, there should have been very little to see at all. Before we move further, let me ask you something simple, the kind of question that gently anchors a moment. Where are you listening from right now? Not in terms of coordinates or addresses, but just your little patch of the planet. And what time is it there? It's always slightly amusing and quietly profound to think that a conversation about the size of the universe is happening at many different local times at once. Night in one place, morning in another, afternoon somewhere else entirely. All of us moving through the same cosmos at different angles of rotation, sharing the same sky, even if it looks different from where we stand. If you find this voice steady, or the ideas soothing, or if this becomes a comfortable part of your evening routine, you're welcome to like the video or subscribe. It helps this calm corner of science reach other people who might need something unhurried and thoughtful before sleep. There's no pressure, just a quiet invitation. Now, let's begin easing into the story itself. For most of human history, the universe felt small in a very practical sense. The sky was vast, certainly, but distant in a way that didn't invite measurement. Stars were lights fixed to a dome. The dark between them wasn't a place, it was simply absence. Even when early astronomers began to map the motions of planets and chart the regularity of the heavens, the universe was still something that fit, conceptually at least, within a finite sphere. It had structure, order, and boundaries, even if those boundaries were imagined rather than observed. As telescopes improved, that sense of containment started to loosen. Stars multiplied, nebulae appeared. Faint smudges resolved into distant systems of stars. The Milky Way turned out not to be the universe itself, but one galaxy among many. Each step outward forced a recalibration, not just of distance, but of expectation. Still, even as the universe grew larger in our models, there was a quiet assumption beneath it all, that while it was very big, it was at least conceptually manageable, that we had a reasonable grasp of how quickly structures formed, how long galaxies took to assemble, and how empty the early universe should have been. Modern cosmology rests on a few core ideas that shape how we interpret what we see. One of them is that the universe has a finite age, about 13.8 billion years according to the best current measurements. Another is that light travels at a finite speed. This means that when we look far away, we're also looking back in time. A galaxy seen at a distance of 10 billion light-years is not being observed as it is now, but as it was 10 billion years ago. distance and time are intertwined in observation, inseparable in practice. There is also the idea of expansion. Space itself is stretching, carrying galaxies along with it. This expansion is not like an explosion from a single point into empty surroundings. It is more subtle. Every region of space grows farther from every other region over time. The farther away something is, the faster it appears to recede. This relationship is built into the structure of space-time itself and shapes everything we observe on the larger scales. From these ideas, astronomers developed a picture of the early universe as a place that was hot, dense, and relatively uniform, gradually cooling and clumping under the influence of gravity. Small fluctuations grew into larger structures. Gas collected, stars ignited, galaxies formed slowly, merging and evolving over billions of years. According to this picture, there should be a certain rhythm to cosmic history, a predictable progression from simplicity to complexity. What James Webb brought into focus was not a contradiction of this framework, but a tension within it. When it looked deep into the early universe, it found galaxies that were already massive, structured, and chemically evolved at times when, by earlier expectations, they should have been much smaller and less developed. These weren't faint, barely there collections of stars. Some appeared surprisingly bright. Some showed signs of organization that suggested rapid formation. This doesn't mean the universe suddenly got bigger in a literal sense because of one telescope. Space did not expand overnight. What changed was our understanding of how much could fit into the early universe, how quickly complexity could arise, and how densely packed the observable cosmos might actually be. When you find more things than expected in a given volume of space, especially at early times, it suggests that either structures formed faster, or that there are more regions like this than previously assumed. Both interpretations quietly push the scale outward. There is an important distinction here that's easy to miss. Astronomers often talk about the observable universe, which is the portion of the cosmos from which light has had time to reach us since the beginning. This observable region has a radius of about 46 billion light-years, even though the universe is only 13.8 billion years old, because space has been expanding while the light was travelling. Beyond that observable boundary, there may be more universe, perhaps much more, but it's not accessible to observation in principle, given the current structure of space-time. James Webb does not see beyond the observable universe. No telescope can. What it does is fill in that observable volume more thoroughly than before, especially at its distant edges. When those edges turn out to be more populated than expected, it changes the statistical picture. The observable universe starts to feel less like a sparse frontier, and more like a crowded city glimpsed from far away, already busy earlier than anticipated. Another subtle shift comes from wavelength. James Webb observes primarily in infrared light. This matters because light from the early universe has been stretched by cosmic expansion. What began as ultraviolet or visible light arrives at Earth as infrared. Earlier telescopes struggled to detect this stretched light with sufficient sensitivity. Webb was designed specifically for this task. Its mirror, instruments, and orbit allow it to collect faint infrared signals with remarkable clarity. That clarity reveals not just the presence of distant galaxies, but details about their mass, star formation rates, and chemical composition. Heavier elements, formed inside stars, indicate multiple generations of stellar life. Seeing them early implies that stars formed, lived, and died quickly enough to enrich their surroundings in a relatively short cosmic time. This compresses timelines and suggests that the early universe was more active than previously assumed. When timelines compress, spatial implications follow. Faster formation across many regions implies that large-scale structure may have emerged efficiently over vast distances. The universe doesn't just get older in this picture, it gets fuller. More things happen in less time, across more space, than earlier models comfortably allowed. All of this feeds into the central idea we're exploring tonight. Not that the universe suddenly became infinite, or that its true size has been definitively measured, but that our previous sense of scale may have been conservative. The cosmos may have always been this vast and dynamic. We are simply better at noticing now. It's worth pausing on how quiet this realization actually is. There's no single image that proves the universe is bigger, no dramatic boundary crossed. Instead, there's an accumulation of data points that gently refuse to fit into a smaller box. Each observation nudges the edges outward. Each revision adds a little more room. For now, it's enough to sit with the idea that the universe did not suddenly reveal itself all at once. It allowed itself to be seen a little more clearly, and in doing so, it reminded us that even our largest concepts are provisional. As this settles in, there's no need to hold on to every detail. Let the sense of scale do its quiet work in the background. Before we can talk about how big the universe really is, we have to slow down and spend time with something that seems very familiar, almost ordinary, yet turns out to be the most important measuring tool we have: light. Not light as a metaphor, not light as something poetic or symbolic, but light as a physical phenomenon, moving through space with very specific rules. Every estimate of cosmic size, every claim about distance, every statement about how far away something is rests quietly on how well we understand light and how carefully we listen to what it tells us. In everyday life, light feels instantaneous. You flip a switch and the room is bright. You look out a window and see the street without delay. Even when we know intellectually that light takes time to travel, that knowledge rarely affects how we experience the world. At human scales, the speed of light is so fast that delays are negligible. It circles Earth more than 7 times in a single second. It travels from the moon to Earth in a little over 1 second. These distances feel vast to us, yet to light, they are barely worth mentioning. Cosmic distances are different. When the universe becomes the setting, light speed stops feeling infinite and starts acting like a strict limit. Light does not rush to fill space instantly. It moves, patiently and consistently, at about 300,000 kilometers per second. Always the same speed, never faster, never slower. That single fact shapes the entire way we observe the universe. When astronomers look at something far away, they are not seeing it as it is now. They are seeing it as it was when the light began its journey. This is not an approximation or a philosophical idea. It is a direct consequence of light's finite speed. A star 10 light-years away is seen as it was 10 years ago. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. Distance and time are locked together in observation, inseparable. This immediately gives light a dual role. It carries information about where something is and when it was. In fact, at large scales, those two pieces of information cannot be separated. To measure distance, we are also measuring age. To look farther is to look earlier. Light becomes a kind of natural archive, storing the history of the universe in transit. But how does light tell us distance in the first place? After all, light itself does not arrive with a label saying how far it travelled. Photons do not carry timestamps. The universe does not provide mile markers. Everything has to be inferred indirectly, using physical laws that remain consistent across space and time. The first and simplest method astronomers use relies on brightness. If you know how bright something truly is, and you observe how bright it appears, you can calculate how far away it must be. This is the same principle you use when judging how far away a streetlight is at night. A distant light appears dimmer not because it is weaker, but because its light spreads out as it travels. The farther it goes, the more space it fills, and the less intense it appears at any one point. In astronomy, objects with known intrinsic brightness are called standard candles. Certain types of stars, such as Cepheid variables, pulse in brightness at a rate that directly correlates with how luminous they are. By observing the rhythm of their pulsations, astronomers can determine their true brightness, compare it to how bright they look from Earth, and calculate distance. This method works well within nearby galaxies, and helped establish the scale of the local universe. For much greater distances, astronomers rely on supernovae, particularly type Ia supernovae. These are explosions of white dwarf stars that reach nearly the same peak brightness every time. They are bright enough to be seen across billions of light years. By treating them as extremely luminous standard candles, astronomers have mapped the expansion of the universe itself. This is how we learn that cosmic expansion is accelerating. Brightness, however, is only one way light carries information. Colour, or more precisely wavelength, plays an equally important role. Light stretches as it travels through an expanding universe. This stretching shifts its wavelength toward the red end of the spectrum, a phenomenon known as redshift. The more space is expanded while the light was travelling, the more stretched it becomes. Redshift acts as a cosmic ruler in a different way. Instead of measuring distance directly through brightness, it measures how much the universe has expanded since the light was emitted. For nearby objects, redshift corresponds closely to velocity. The farther away a galaxy is, the faster it appears to be moving away from us due to expansion. This relationship is known as Hubble's law. At very large distances, redshift becomes less about speed in the ordinary sense, and more about the history of expansion itself. Space between galaxies grows while the light is in transit, continuously stretching the wavelength. A galaxy observed at high redshift is not just far away. It is seen at a time when the universe was much younger and smaller. This is where light stops being a simple messenger and starts acting like a layered record. Its brightness tells us about distance. Its wavelength tells us about expansion. Its spectrum, the detailed breakdown of wavelengths, tells us about composition, temperature, and motion. All of this information arrives together, encoded in the same stream of photons. James Webb was designed specifically to read this code more carefully than any telescope before it. Because it operates primarily in the infrared, it is tuned to detect light that has been stretched dramatically by cosmic expansion. Light that began its journey as ultraviolet radiation from young stars in the early universe arrives at Earth as faint infrared signals. Webb's instruments are optimized to collect those signals without losing detail. This matters because earlier telescopes could see only the brightest, most extreme objects at great distances. Much of the early universe remained below the detection threshold. It wasn't invisible because it wasn't there. It was invisible because our rulers were too blunt. We were trying to measure a delicate structure with tools designed for closer work. When Webb began observing, it didn't just extend our reach slightly farther, it sharpened the ruler itself. It allowed astronomers to distinguish between objects that had previously blended together. It provided more accurate measurements of redshift, mass, and star formation. And as those measurements accumulated, a pattern began to emerge. Galaxies at very high redshift appeared more numerous and more massive than expected. According to earlier models, the early universe should have been relatively sparse, with small, irregular galaxies slowly assembling into larger ones over time. Webb's observation suggested that this assembly happened efficiently and quickly, across wide regions of space. This doesn't mean the laws of physics changed. Gravity still works the same way. Nuclear fusion still powers stars. What changes is our understanding of how those processes played out across immense distances under early conditions. When light reveals mature structures where only primitive ones were expected, it implies that the universe was capable of building complexity over vast scales earlier than assumed. There is another subtle way light becomes a ruler, one that involves geometry rather than brightness or colour. The cosmic microwave background, the faint afterglow of the early universe, provides a reference pattern imprinted across the sky. Tiny variations in its temperature correspond to sound waves that travelled through the hot plasma of the early universe. The size of these variations acts as a standard ruler. By measuring how large they appear today, astronomers can infer the geometry and overall scale of the universe. This method does not measure distance to individual galaxies, but it sets the framework within which all other distances are interpreted. It tells us whether space is flat, curved, or closed on large scales. Current measurements suggest that space is very close to flat, meaning that parallel lines remain parallel and the universe does not curve back on itself in any obvious way. A flat geometry combined with accelerated expansion implies something important. The observable universe is only a portion of the whole. Beyond what we can see, space likely continues, perhaps infinitely, or perhaps in a way that exceeds any practical measure. Light sets the boundary of what we can know directly. Everything beyond that boundary exists, if it exists at all, outside observational reach. When James Webb reveals that the observable universe is more densely populated and structured than expected, it quietly suggests that the unobservable regions, whatever their nature, may be even more extensive. If complexity arises easily and early within the visible portion, there is no obvious reason to assume it stops abruptly beyond it. None of this requires dramatic reinterpretation in a single moment. Science rarely works that way. Instead, it is a slow adjustment of scales. Light, serving faithfully as our ruler, keeps reporting values that sit slightly higher than anticipated. Distances are confirmed, redshifts align, mass estimates rise. Each measurement alone fits within uncertainty. Together, they lean in the same direction. As you take this in, there is no need to visualize the entire universe or to hold precise numbers in mind. What matters is the method. Light does not exaggerate, it does not speculate. It arrives exactly as physics allows, carrying information shaped by the journey it took. When our instruments improve, we don't change what light says, we simply hear more of it. As light quietly takes on the role of our measuring tool, another idea naturally comes into view, one that sounds simple at first, but turns out to be deeply restrictive in a very physical way. No matter how powerful our telescopes become, no matter how patient we are, there is a limit to what we can observe. Not because of technology, not because of human shortcomings, but because of the structure of the universe itself. This limit defines what physicists call the observable universe, and understanding it requires setting aside the instinct to think of space as something static and unlimited. It's tempting to imagine the universe as a vast stage where everything exists simultaneously, just waiting to be discovered, if we could only look far enough. But observation does not work that way. Every piece of information we receive arrives on a delay, carried by light or other signals that obey strict speed limits. The observable universe is not defined by where things are now. It is defined by how far information has had time to reach us. To make sense of this, it helps to slow down and separate a few ideas that often blur together. One is age. The universe has a finite age, about 13.8 billion years according to current measurements. Another is distance. Light has been travelling for that same amount of time since the earliest moments when the universe became transparent. A third is expansion. Space itself has been stretching while the light was in transit. These three facts combine in a way that makes the observable universe larger than you might expect from age alone. If the universe were not expanding, the farthest we could see would be about 13.8 billion light-years in every direction. That would be the maximum distance light could have travelled since the beginning. But because space expands, the galaxies that emitted that light are now much farther away than where they were when the light began its journey. While the light was moving forward, the space it was crossing was also growing. The result is that the radius of the observable universe today is about 46 billion light-years. This number can feel counterintuitive at first. How can something be farther away than the age of the universe multiplied by the speed of light? The answer lies in understanding that the expansion of space does not violate the speed limit of light. Galaxies are not racing through space faster than light. Instead, space itself is stretching, increasing the distance between points without requiring anything to locally exceed that limit. Light still moves through its immediate surroundings at the same speed. The surroundings themselves just change while it travels. The observable universe, then, is a sphere centered on the observer, defined not by where matter exists, but by how far information has had time to propagate. It is a horizon, not a boundary. There is nothing special about the edge itself. It does not mark the end of the universe. It simply marks the limit beyond which signals have not yet arrived. An important detail often overlooked is that this horizon is observer-dependent. If you were located in a distant galaxy billions of light years away from Earth, your observable universe would be centered on you, not on us. You would see regions of space we cannot, and you would be unable to see some regions that we can. Each observer carries their own observable universe with them, defined by their position in space-time. This immediately tells us something important about size. When we talk about the size of the universe, we're almost always talking about the size of the observable universe, not the universe as a whole. The total universe could be much larger. It could even be infinite. The observable portion is simply the part we have access to, constrained by physical law. There is another horizon that deepens this limitation further, one that looks not just backward but forward. Because the expansion of the universe is accelerating, there are regions of space from which light emitted today will never reach us, no matter how long we wait. This defines what is known as the cosmic event horizon. It marks the ultimate limit of future observability. Even though the observable universe is growing with time as more light reaches us from farther regions, there are distant galaxies that are already receding so rapidly due to expansion that any light they emit now will never cross the expanding gap. They exist, but they are permanently beyond our reach. The observable universe, in this sense, is not simply incomplete. It is selectively incomplete. James Webb operates entirely within these limits. It does not break horizons or peer beyond them. What it does instead is push our observations closer to the boundary in time, capturing light that has been travelling since the universe was only a few 100 million years old. This is close to the earliest era when stars and galaxies could form at all. In earlier observations, this region near the observational horizon appeared relatively sparse. There were galaxies, but fewer than expected, and many were faint and poorly resolved. Models of cosmic structure formation predicted that this region should be dominated by small, irregular systems still in the early stages of assembly. What Webb revealed was not a sudden expansion of the horizon itself, but a surprising richness within it. The boundary did not move, but the contents inside it multiplied. When astronomers counted galaxies at high redshift using Webb's data, they found more of them than predicted by earlier models. Not just more points of light, but more massive systems, with higher star formation rates and more advanced structure. This has subtle implications for size. If the observable universe contains more matter, more stars, and more galaxies at early times than previously thought, then the processes shaping it must have operated efficiently across vast regions. This suggests that large-scale structure emerged quickly and broadly, filling space more thoroughly than anticipated. There is also a statistical implication. Cosmological models often assume that the observable universe is representative of the universe as a whole on large scales. This assumption is called the cosmological principle, the idea that the universe is homogeneous and isotropic when viewed at sufficiently large scales. In simple terms, no region is special. The observable universe is assumed to be a fair sample. If that assumption holds, then discovering greater density and complexity within the observable universe suggests that similar richness extends beyond it. Not because we can see it, but because the laws shaping it do not abruptly change at the horizon. The horizon limits our knowledge, not the universe's behaviour. It is worth emphasising that none of this implies certainty about the total size of the universe. Physics is careful about such claims. What it implies is a shift in plausibility. Smaller universes, in the sense of ones with limited extent beyond what we can see, become less favoured. Larger universes, possibly vastly larger, fit more comfortably with observations that show efficient structure formation early and across wide volumes. The observable universe also introduces a limit on causality. There are regions within it that were never in causal contact with each other in the early universe. This means that they could not have exchanged information or influenced each other directly. Yet they exhibit remarkably similar properties, such as nearly uniform temperature in the cosmic microwave background. This puzzle is addressed by the theory of cosmic inflation, which proposes a brief period of extremely rapid expansion in the early universe. Inflation would have stretched a small, causally connected region to enormous size, explaining the observed uniformity. Inflation also predicts that the universe should be much larger than the observable portion, potentially enormously so. James Webb does not directly observe inflation, but its findings are consistent with a universe where early conditions were capable of producing widespread structure quickly. When combined with inflationary theory, this reinforces the idea that what we see is only a fraction of what exists. Another physical limit worth considering is resolution. Even within the observable universe, there are scales we cannot probe directly. Very small structures in the early universe are smoothed out by observational constraints. Light from small, faint objects may blend together or fall below detection thresholds. Webb improves resolution and sensitivity, but it does not eliminate these limits entirely. What it does do is reduce uncertainty. When uncertainty decreases and observations consistently land near the upper end of predicted ranges, theoretical models must adapt. In cosmology, adaptation often means expanding parameter space rather than discarding frameworks entirely. The universe accommodates these changes by becoming, effectively, larger in scope. It's also important to recognize that the observable universe is dynamic. Over time, as light continues to arrive from farther regions, the observable volume grows. However, because of accelerating expansion, this growth will eventually slow and stop. There is a finite amount of information that will ever reach us. This gives the observable universe a slightly paradoxical character. It is both expanding and limited. It grows toward a fixed asymptote, a maximum reach defined by cosmic expansion. The universe beyond that reach may continue indefinitely, but our access to it will not. James Webb operates during a relatively brief window in cosmic history, when deep observation is still possible. In the far future, distant galaxies will fade beyond detectability as expansion stretches their light beyond observable wavelengths. Civilizations arising trillions of years from now may see a much emptier sky, unaware of the vast cosmos that once filled it. This context adds weight to current observations. When Webb shows us that the early observable universe was rich and structured, it is not merely adding data, it is capturing a fleeting opportunity to understand the scale of existence before expansion hides much of it permanently. It's helpful to let go of the notion that the universe has an edge we are approaching. The observable universe is not a wall. It is a moving horizon shaped by time, expansion, and the speed of light. Its limits are not spatial in the ordinary sense, they are causal. Once the idea of an observable universe settles into place, the next step follows almost automatically. If there is a horizon defined by how far light can travel, then the behavior of space itself becomes impossible to ignore. The universe is not simply sitting there, waiting to be measured. It is changing continuously, and that change alters every distance we try to define. Expansion is not a background detail in cosmology. It is the central process that reshapes how size, motion, and time relate to one another. At first glance, expansion sounds like something familiar. We picture an explosion, matter rushing outward into empty space, leaving a growing bubble behind. That image feels intuitive, but it leads us in the wrong direction almost immediately. The expansion of the universe is not matter flying away from a central point. There is no center. There is no surrounding emptiness that the universe is expanding into. Expansion happens everywhere at once. Every region of space stretches relative to every other region. A more accurate way to think about it is to imagine distances themselves changing. Two galaxies that are not gravitationally bound to each other will, over time, find the space between them increasing. They are not pushing away from each other through space. Space itself is increasing between them. This distinction matters because it explains why expansion does not violate the speed of light. Objects can become separated faster than light without ever locally moving faster than light through their immediate surroundings. This stretching of space is subtle at small scales. Inside galaxies, gravity dominates. Stars orbit normally. Solar systems remain intact. Even clusters of galaxies can resist expansion locally. But at larger scales, beyond these gravitationally bound systems, expansion becomes the dominant influence. Over millions and billions of light years, it shapes the structure of the universe. The first clear evidence for this expansion came from observing light. When astronomers examined the spectra of distant galaxies, they noticed that the characteristic lines produced by known elements were shifted toward longer wavelengths. This shift, called redshift, was systematic. The farther away a galaxy appeared to be, the more its light was shifted toward the red end of the spectrum. At first, this was interpreted as a Doppler effect, similar to the way a siren sounds lower in pitch as an ambulance drives away, and at small distances this interpretation works reasonably well. Nearby galaxies do move relative to us through space, and that motion contributes to redshift. But as distances increase, the Doppler explanation becomes incomplete. At cosmological scales, redshift is dominated not by motion through space, but by the expansion of space itself. As light travels, the space it occupies stretches. The wavelength of the light stretches with it. By the time the light reaches us, it has been lengthened, sometimes dramatically. This stretching carries direct information about how much the universe has expanded during the light's journey. Redshift, then, is not just a measure of speed. It is a measure of cosmic history. A higher redshift means the light was emitted when the universe was smaller. Each increment in redshift corresponds to a specific stage in the expansion timeline. Astronomers use this relationship to reconstruct how the universe has grown over time. What James Webb contributes here is precision. Earlier telescopes could measure redshift for very distant objects, but often with significant uncertainty. Faint signals blur together. Spectral lines become difficult to distinguish. Webb's infrared sensitivity allows it to detect and separate these stretched wavelengths more clearly, even when the signals are extremely weak. As Webb measured redshifts for galaxies thought to exist very early in cosmic history, it confirmed that many of them were indeed from epochs close to the beginning of galaxy formation. This ruled out simpler explanations that they were closer, dimmer objects masquerading as distant ones. The universe was not playing a trick of perspective. These galaxies really were ancient. What made this surprising was not just their existence, but their properties. Some appeared massive, some showed signs of mature stellar populations. This implied that expansion did not prevent rapid structure formation. Space may have been stretching quickly, but gravity was still efficient at pulling matter together across large regions. This interplay between expansion and gravity is delicate. Expansion tries to increase distances, gravity tries to decrease them. The balance between the two determines what structures form and how large they become. In the early universe, conditions favoured rapid growth of structure, especially in regions with slightly higher density. Dark matter, which interacts gravitationally but not through light, provided scaffolding that helped ordinary matter clump together quickly. Expansion also affects how we define distance itself. In everyday experience, distance is straightforward. A meter today is a meter tomorrow. In cosmology, distance depends on when you measure it. The distance to a distant galaxy now is greater than the distance was when the light we see left it. There are several different definitions of distance used in cosmology. each useful for different purposes. There is comoving distance, which factors out expansion and remains fixed for objects moving with the cosmic flow. There is proper distance, which changes with time as space expands. There is luminosity distance, which relates to brightness. There is angular diameter distance, which relates to apparent size. These distances can behave in ways that seem counterintuitive, especially at high redshift. For example, beyond a certain distance, objects can appear larger on the sky even as they are farther away. This happens because angular diameter distance reaches a maximum and then decreases with redshift in an expanding universe. Such effects are not quirks, they are direct consequences of how space stretches over time. James Webb's observations operate within this framework. When it detects a galaxy at high redshift, astronomers translate that redshift into multiple distance measures depending on what they are studying. Size, mass, brightness, and age all depend on understanding how expansion has altered the light's journey. Expansion also introduces the concept of scale factor, a mathematical description of how the size of the universe changes over time. At early times, the scale factor was small. As time passes, it grows. Redshift is directly related to the inverse of the scale factor at the time of emission. This gives redshift a clean theoretical interpretation. It is not arbitrary. It is tied to the universe's overall growth. One of the most significant discoveries in cosmology is that expansion is accelerating. Observations of distant supernovae revealed that the universe is not just expanding, but doing so faster over time. This acceleration is attributed to dark energy, a form of energy associated with space itself. Dark energy does not clump. It does not dilute as space expands. Instead, it maintains a roughly constant density, causing its influence to grow as the universe becomes larger. This acceleration affects redshift distance relationships at high values. It changes how quickly galaxies move beyond our observational reach. It also affects how long light can travel before expansion carries its source beyond the cosmic event horizon. When James Webb shows us galaxies at very high redshift, it is showing us objects that formed before dark energy dominated the universe's behaviour. At those early times, matter controlled expansion more strongly. Structure formation was vigorous. The universe was smaller, denser, and more active. Seeing so much complexity during this era reinforces the idea that large-scale structure was already widespread when the universe was only a fraction of its current age. All of this feeds back into our sense of size. Expansion means that size is not a fixed number. The universe today is larger than it was yesterday. The distances between unbound galaxies are increasing continuously. When we say the universe is big, we are making a statement that depends on when we are asking the question. James Webb does not freeze the universe in place. It samples different moments along the expansion timeline. By doing so, it helps us understand not just how big the universe is now, but how quickly it grew into that size. There is also a psychological adjustment required here. Human intuition is built for static environments. We are comfortable with objects that stay where they are. Expansion asks us to think in terms of relationships that change even when nothing is moving locally. Space itself becomes an active participant. As this becomes familiar, it becomes easier to accept that the universe's size is not something we simply measure once and record. It is something we track, interpret, and revise as our observations improve. Redshift is the quiet bookkeeping system that keeps this process consistent. It links light to expansion, expansion to time, and time to structure. At first, it feels natural to think that distance and time are interchangeable when we talk about the universe. Light travels at a fixed speed, so if something is 1 billion light years away, it must be 1 billion years in the past. Simple, clean, comforting. And for a while, this way of thinking works well enough to get started. But as soon as expansion enters the picture in a serious way, that neat relationship begins to loosen. Distance stops being a single number and time stops lining up in a straight, predictable way. What seems like a simple ruler turns out to be a flexible tape measure, stretching while you're trying to read it. To understand why distance is not the same as time, it helps to return to something very basic and then slowly complicate it. Light does take time to travel. That part never changes. A photon emitted from a distant galaxy spends years, millions of years, or billions of years moving through space before reaching us. That travel time is real. It is fixed. Once the light arrives, that duration is settled forever. In that sense, time is straightforward. Distance, however, is not. Distance depends on when you ask the question. Imagine a galaxy that emitted light when the universe was very young. At the moment that light was released, the galaxy was much closer to the region of space that would eventually become Earth. While the light was travelling, the universe expanded, space stretched. The galaxy moved farther away, not because it was racing through space, but because space itself was growing. By the time the light arrives, the galaxy is vastly farther away than it was when the journey began. So what is the distance to that galaxy? Is it the distance when the light was emitted? The distance when the light was halfway here? Or the distance now, when we finally observe it? All three are valid in different contexts. None of them are identical. This is the first crack in the idea that distance and time can be treated as the same thing. In everyday life, distance does not change just because time passes. A mountain remains the same number of kilometers away whether you measure it now or an hour from now, assuming neither of you moves. In cosmology, the background itself changes. Space is dynamic. Distances between unbound objects increase simply because the universe ages. This means that a single light travel time corresponds to multiple distances, depending on how you define them. Astronomers are very careful about this, even if popular descriptions sometimes gloss over it. When James Webb observes a galaxy that existed 13 billion years ago, that galaxy is not 13 billion light-years away in the present-day sense. It is much farther, roughly 30 to 40 billion light-years away, depending on the details of the cosmological model used. This difference is not a technicality. It is central to why the universe feels larger than simple intuition suggests. One useful concept here is comoving distance. This is a way of defining distance that factors out expansion. In comoving coordinates, galaxies that are moving with the expansion of the universe stay at fixed positions. Their comoving distance does not change over time. This is useful for mapping large-scale structure and comparing positions across cosmic history. Another concept is proper distance, which is the distance between 2 points at a specific moment in cosmic time. Proper distance changes as the universe expands. The proper distance to a distant galaxy today is greater than it was in the past, even if the galaxy itself has not moved through space. Light travel time corresponds to neither of these distances directly. It corresponds to the integral of expansion over time. In simpler terms, the photon experiences a continuously changing environment as it travels. It does not move through static space. It moves through space that stretches while it moves. This is why saying the galaxy is X light-years away is often shorthand, not a precise statement. What is usually meant is that the light has travelled for X years. That is a time measurement, not a present-day distance measurement. The two diverge more dramatically the farther back you look. Redshift adds another layer. Redshift tells us how much the universe has expanded since the light was emitted. Two galaxies can have similar light travel times but different redshifts if the expansion history differs along their lines of sight. This happens because expansion is not uniform in time. It has changed rate over cosmic history, slowing during matter-dominated eras and accelerating more recently due to dark energy. As a result, time does not map linearly onto distance. A small change in redshift at high values can correspond to a large change in distance, while the same change at low redshift corresponds to a much smaller one. The universe stretches unevenly across time, and distance reflects that stretching. James Webb operates primarily at high redshift, where these effects are strongest. When it detects galaxies at redshifts of 10, 12, or even higher, it is observing light that left when the universe was only a few 100 million years old. The travel time is enormous. The present-day distance is even more enormous. And the relationship between the two is shaped by the entire expansion history of the universe. This is why Webb's findings quietly shift our sense of scale. When galaxies appear earlier than expected, fully formed and abundant, it implies that large regions of space were already participating in structure formation very quickly. Those regions are now separated by vast distances due to expansion. The universe did not just age, it grew apart. Another reason distance and time diverge is acceleration. If expansion were constant, the relationship between time and distance would still be complex, but at least predictable in a simple way. Accelerating expansion changes that. As dark energy becomes dominant, space stretches faster at later times. Light emitted at different epochs experiences different expansion regimes. This means that two photons emitted the same amount of time ago can end up associated with different present-day distances depending on when most of their journey occurred. Light that spent more time travelling during the accelerating era experiences more stretching of space than light that travelled mostly during earlier eras. There is also a conceptual trap here that's worth addressing gently. It is tempting to imagine light leaving a galaxy and travelling through a fixed landscape, while the galaxy itself moves away. That picture sneaks motion through space back into the story. In reality, the photon is not chasing a retreating galaxy. The galaxy is not running away from the photon. Both are embedded in expanding space-time. The photon's path is defined by the geometry of space-time. It always moves locally at the speed of light. Expansion changes the geometry, not the speed. This is why it is possible for light emitted by a galaxy that is now receding faster than light to still reach us, as long as the expansion rate between us and the galaxy was lower earlier in its journey. This also explains why there are galaxies we can see whose current recession speed exceeds the speed of light. This does not violate relativity because the speed limit applies to motion through space, not to the expansion of space itself. Once again, distance stops behaving like a simple number you can attach to an object. James Webb's observations often involve galaxies near or beyond the point where naive intuition would suggest they should be unreachable. Yet the light arrives because the expansion history allowed it to do so. When astronomers calculate distances to these galaxies, they are careful to specify which distance they mean. Light travel time, co-moving distance, proper distance now, proper distance then. Each tells a different story. Time, on the other hand, is unambiguous in one crucial sense. Once the light arrives, the duration of its journey is fixed. The universe cannot change how long the photon travelled. That time is locked in. Distance, however, continues to evolve. The galaxy keeps getting farther away even after we see it. The distance now is greater than the distance when we observed it, and that distance will continue to increase as long as expansion continues. This leads to a subtle but important realization. When we look deep into the universe, we are never seeing a map of where things are. We are seeing a layered history of where things were, projected onto our present moment. The deeper we look, the more those layers compress in time while spreading out in distance. This compression is part of why the early universe can feel crowded in observations. Many events that occurred across a wide range of distances are squeezed into a relatively narrow time window near the beginning. James Webb reveals this by showing many galaxies existing within the first billion years. In time, that era feels brief. In space, it spans enormous volumes. This mismatch between time and distance is also why phrases like edge of the universe are misleading. The observable universe has a temporal boundary more than a spatial one. It marks the limit of how far back we can see, not a physical edge in space. Distance keeps increasing beyond that boundary, but the information does not reach us. It is also why the universe can be both finite in age and effectively limitless in extent. A finite amount of time does not imply a finite amount of space when space itself expands. Distance is not capped by time alone, it is shaped by how space behaves during that time. James Webb's role in all of this is not to rewrite these principles, but to make their consequences unavoidable. When you see galaxies that formed early and are now unimaginably far away, the separation between time and distance becomes concrete. The universe did not wait to grow large before building complexity. It did both at once. As this settles, it becomes easier to let go of the idea that distance tells you when something happened. It tells you where something is now, in a universe that does not stand still. Time tells you when the light left. Redshift tells you how much the universe changed in between. All three are needed. None can substitute for the others. To understand what James Webb measures that earlier instruments could not, it helps to step away from the idea that telescopes simply take pictures. A telescope is not primarily a camera, it is a measuring device. Every image it produces is the visible surface of a deeper process, one where light is collected, sorted, compared, and interpreted according to physical rules. What makes James Webb different is not that it sees farther in a vague sense, but that it measures specific properties of light with a level of sensitivity and precision that changes what questions can be asked in the first place. Earlier space telescopes, especially those operating in visible and near-infrared light, were extraordinarily successful at mapping the nearby and intermediate universe. They revealed galaxies, nebulae, and large-scale structure in exquisite detail. They measured distances, motions, and compositions well enough to establish the basic framework of modern cosmology. But they were working close to the limits imposed by wavelength, detector sensitivity, and background noise. As observations pushed toward earlier cosmic times, the signals became faint, stretched, and ambiguous. James Webb was designed explicitly to operate in that difficult regime. It does not simply extend the reach of previous instruments by a small margin, it shifts the measurement space into a different part of the electromagnetic spectrum and combines that shift with a collecting area and thermal stability that make previously inaccessible signals usable. The most fundamental difference lies in wavelength. James Webb observes primarily in the infrared, extending well beyond what earlier major space telescopes could measure effectively. This is not a cosmetic choice. It is a physical necessity. Light from the early universe is stretched by cosmic expansion. Ultraviolet and visible photons emitted by the first generations of stars and galaxies arrive today as infrared photons. If you cannot measure infrared light with sufficient sensitivity, you are effectively blind to much of the early universe. Earlier telescopes could detect some of this stretched light, but only the brightest sources. Many early galaxies were simply too faint, their signals lost in noise or blended into the background. Webb's infrared detectors are designed to operate at extremely low temperatures, reducing thermal noise to levels where faint cosmic signals can be isolated. This allows it to measure light that would have been indistinguishable from instrumental background in earlier systems. Another crucial difference is spectral resolution. Measuring that a galaxy exists is only the first step. To understand what it is, how massive it is, how old its stars are, and how fast it is forming new ones, astronomers need spectra. A spectrum spreads light out by wavelength, revealing absorption and emission features produced by atoms and molecules. These features act like fingerprints, encoding physical conditions at the source. James Webb carries instruments capable of producing high-quality spectra for extremely faint and distant objects. Earlier telescopes could often obtain spectra only for relatively bright galaxies or for integrated light over large regions. Webb can isolate individual sources at high redshift and measure their spectra directly. This changes distance estimates from indirect guesses into precise determinations. Redshift measurements are a clear example. Without spectra, redshift estimates rely on photometry, measuring brightness through different filters and fitting models. This method is useful but uncertain, especially at high redshift where different physical scenarios can produce similar colours. Webb's spectroscopic capabilities allow astronomers to identify specific spectral lines and measure redshift unambiguously. This removes a major source of uncertainty in early universe studies. Mass measurement is another area where Webb changes the picture. The mass of a distant galaxy cannot be measured directly. It must be inferred from its light, its dynamics, or its gravitational influence. Light alone is a tricky proxy. Young stars are bright but not very massive. Older stars are dimmer but contribute more mass. Dust can obscure light. Gas emits in specific wavelengths. Untangling these components requires detailed spectral information across multiple wavelengths. Webb's infrared coverage allows astronomers to sample stellar populations more completely. Light from older, cooler stars peaks in the infrared. Earlier telescopes often underestimated stellar mass in distant galaxies because they could not see this component clearly. Webb reveals that some early galaxies contained far more stellar mass than expected, simply because earlier measurements were missing part of the picture. Star formation rates are also measured differently with Webb. Young stars emit strongly in ultraviolet, but that light is easily absorbed by dust. The absorbed energy is then re-emitted in infrared wavelengths. Webb can detect this re-emitted light, providing a more accurate measure of how much star formation is actually occurring. This leads to higher inferred star formation rates in many early galaxies, again contributing to the sense that the early universe was more active and crowded than previously thought. Chemical composition is another key measurement. The presence of elements heavier than hydrogen and helium indicates that stars have already lived and died, enriching their surroundings. Measuring metallicity in distant galaxies requires detecting specific spectral lines that are often shifted into the infrared. Webb's sensitivity allows these measurements to be made at redshifts where they were previously inaccessible. When Webb detects relatively high metallicity in very early galaxies, it implies that multiple generations of stars formed quickly. This compresses the timeline of chemical evolution and suggests that large regions of space underwent rapid enrichment. That, in turn, implies efficient structure formation across large volumes. Webb also measures morphology differently. At high redshift, galaxies appear small and faint. Earlier telescopes often saw them as irregular blobs. Webb's resolution in the infrared allows astronomers to resolve structure within these galaxies. Disks, bulges, and clumps become visible. This structural information tells us about how galaxies assembled and how angular momentum was distributed early on. Seeing organized structure at early times challenges models where galaxies grow slowly through repeated mergers. It suggests that some galaxies formed rapidly in relatively smooth processes, drawing in gas efficiently along cosmic filaments. Those filaments themselves span enormous distances, reinforcing the idea that large-scale structure was already well developed. Another measurement Webb excels at is the detection of extremely faint sources near the observational limit. This matters statistically. Cosmology relies heavily on counting objects. How many galaxies exist at a given redshift? How does that number change over time? Earlier telescopes sampled only the brightest tail of the distribution. Webb probes deeper into the population, revealing many more faint galaxies. When number counts increase at high redshift, it affects estimates of total mass, total star formation, and total light output in the early universe. These totals feed into models of cosmic evolution and influence conclusions about how much space was actively forming structure at a given time. Webb also measures the intergalactic medium indirectly. As light from distant sources travels toward us, it passes through clouds of gas. These clouds leave absorption features in the spectrum. By analyzing these features, astronomers can map the distribution of gas between galaxies. Webb's sensitivity allows these measurements at earlier times and lower densities than before. This information is important because the intergalactic medium contains most of the universe's ordinary matter. Its distribution reflects the large-scale structure of space. Seeing how it evolves over time helps constrain how matter flows into galaxies and how energy from stars and black holes feeds back into surrounding space. Earlier telescopes struggled to separate these subtle absorption features from noise at high redshift. Webb's clean infrared spectra make such measurements feasible, again filling in regions of cosmic history that were previously poorly constrained. Another difference lies in stability. Webb operates far from Earth, in a stable thermal environment where temperature fluctuations are minimal. This stability improves calibration and reduces systematic errors. When measuring extremely faint signals, small uncertainties matter. Webb's design minimizes those uncertainties, allowing cumulative measurements to build a reliable picture. All of these capabilities combine to produce a result that feels qualitative, even though it is quantitative. The early universe appears fuller, more galaxies, more mass, more structure, more activity. Not because the universe changed, but because the measurements improved. It is important to be careful here. Webb does not prove that the universe is larger in a literal geometric sense. What it does is show that within the observable universe, there is more content at early times than expected. This pushes models towards scenarios where space was efficiently populated and structured early on. Those scenarios are more naturally accommodated in universes that extend far beyond the observable horizon. In other words, Webb does not measure size directly. It measures density, structure, and timing. Size follows as an implication, not a direct observation. There is also a shift in confidence. Earlier measurements at high redshift often came with large uncertainties. Models could accommodate discrepancies by adjusting parameters within wide error bars. Webb's data narrows those bars. When multiple independent measurements converge on similar conclusions, flexibility decreases. The universe begins to look consistently large, active, and complex very early. As observations continue, some early interpretations will be refined. Mass estimates may adjust. Star formation rates may be revised. But the fundamental change remains. Webb has moved the measurement frontier into a regime where distance, time, and structure intersect most strongly. When the earliest galaxies began to appear, the universe was a very different place from the one we inhabit now. It was hotter, denser, and far more uniform on large scales. There were no long-established spiral disks. No massive elliptical galaxies settled into quiet old age. No familiar cosmic scenery. And yet, when James Webb looked into this early period, it found galaxies that seemed surprisingly mature for their time. Understanding how that could happen requires slowing down and carefully following the physics that governs how structure emerges from an expanding, nearly featureless beginning. In the earliest moments after the universe became transparent to light, matter was distributed almost evenly, with only tiny variations in density. These variations were small, typically 1 part in 100,000, but they mattered enormously. Gravity amplifies differences. Regions that were slightly denser than average exerted a slightly stronger gravitational pull, attracting more matter and becoming denser still. Over time, this runaway process turned faint irregularities into the seeds of cosmic structure. At first, this growth was slow. The universe was expanding rapidly, and expansion works against gravity. As space stretches, it pulls matter apart, making collapse more difficult. Whether a region could grow into a galaxy depended on a balance between its own gravity and the expansion of the universe around it. In the earliest eras, that balance was delicate. Dark matter played a central role in tipping it. Unlike ordinary matter, dark matter does not interact with light. It does not radiate energy. It cannot cool by emitting photons. Because of this, it began clumping earlier and more efficiently than normal matter. Dark matter formed large invisible halos, gravitational wells that ordinary matter could later fall into. These halos provided the scaffolding for galaxy formation. Once ordinary matter, mostly hydrogen and helium gas, fell into these potential wells, it could begin to cool, condense, and eventually form stars. Cooling is essential. Without it, gas remains too energetic to collapse. In the early universe, cooling occurred through simple atomic processes involving hydrogen and helium, and later through heavier elements once stars began enriching their surroundings. What James Webb has revealed is that this process may have proceeded faster and more efficiently than many models assumed. Galaxies observed at very high redshift appear to have accumulated significant mass in a relatively short amount of cosmic time. This suggests that dark matter halos grew quickly and that gas flowed into them effectively, overcoming both thermal pressure and cosmic expansion. One reason this may have happened lies in the structure of the cosmic web. Matter in the universe is not distributed randomly. It forms a network of filaments, sheets, and nodes. Dark matter halos grow at the intersections of these filaments, where matter flows converge. Gas streaming along filaments can feed halos continuously, sustaining high rates of star formation. In the early universe, these filaments were denser and more active. Gas was abundant and relatively pristine. When it flowed into halos, it could fuel rapid growth without being immediately disrupted by feedback from stars and black holes. This created conditions where galaxies could assemble large amounts of mass quickly. Star formation itself may also have been more efficient. The first generations of stars formed from gas with very low metallicity, meaning it contained almost no elements heavier than helium. This changes how gas cools and fragments. Some theories suggest that early star formation favoured more massive stars, which burn brightly and live briefly. These stars would have produced intense radiation and heavy elements quickly, enriching their surroundings and accelerating subsequent star formation. Feedback, the process by which stars and black holes inject energy back into their environment, is another crucial factor. In later galaxies, feedback can regulate growth by heating gas and driving it out of galaxies, slowing star formation. In the early universe, feedback may not have been strong enough initially to halt inflows of fresh gas. The balance between inflow and feedback may have favoured rapid build-up before self-regulation became effective. James Webb's observations of early galaxies showing high star formation rates support this picture. They suggest that gas supply was abundant and that feedback had not yet fully suppressed growth. This leads to galaxies that appear massive and bright at times when earlier models predicted smaller, more chaotic systems. Another factor is merger rate. The early universe was crowded. Distances between halos were smaller because the universe itself was smaller. This made interactions and mergers more frequent. Mergers can rapidly increase galaxy mass and trigger bursts of star formation. If early galaxies merged often, they could grow quickly through hierarchical assembly. However, Webb's data complicates a simple merger-dominated picture. Some early galaxies appear surprisingly ordered, with structures that hint at rotational support rather than purely chaotic assembly. This suggests that smooth gas accretion along filaments played a major role alongside mergers. The physics of angular momentum also comes into play. As gas falls into dark matter halos, it carries angular momentum inherited from the larger-scale tidal field of the universe. How that angular momentum is redistributed determines whether a galaxy forms a disk, a spheroid, or something in between. Efficient angular momentum transport could allow gas to settle into organized structures faster than expected. Cooling times are another important piece. In dense early halos, gas cooling times may have been short compared to dynamical timescales. This allows gas to collapse and form stars rapidly without being held up by thermal pressure. The high density of the early universe naturally shortens these timescales. All of these processes operate within the constraints imposed by expansion. The universe was expanding faster in its early history than it is now. That expansion sets a clock on how much time structures have to grow. When James Webb reveals galaxies that seem large and evolved early, it tells us that the physics driving collapse, cooling, and star formation was able to operate efficiently despite that expansion. This efficiency has implications beyond individual galaxies. If galaxies formed quickly across large regions, it implies that the early universe was not a sparse environment where structure was rare. Instead, it suggests that structure was widespread. Many regions were actively forming galaxies at once. From a statistical perspective, this increases the inferred density of galaxies at early times. A higher number density of galaxies implies that the volume of the observable universe contained more mass and more luminous objects earlier than expected. This does not change the observable boundary, but it changes what fills it. There is also an implication for reionization, the process by which the first stars and galaxies ionize the neutral hydrogen filling the universe. Rapid galaxy formation would have produced large amounts of ultraviolet radiation, contributing to reionization more efficiently. Webb's measurements of early galaxies feed directly into models of how and when this transition occurred. Importantly, none of this requires abandoning the basic framework of cosmology. The laws of gravity, thermodynamics, and nuclear physics remain intact. What changes are the details, the efficiency of gas inflow, the timing of feedback, the role of dark matter substructure. These adjustments shift outcomes significantly without altering fundamentals. As these models adapt, the picture that emerges is one of a universe that was capable of building complexity rapidly across vast distances. That capability makes it easier to accept a universe that is very large in extent. A small universe would struggle to accommodate such widespread early activity without fine-tuning. A large universe accommodates it naturally. James Webb does not measure that size directly, but by showing us what existed early, it forces us to take the implications seriously. If galaxies like these formed quickly and often, then the regions where they formed must have been common, and if those regions are common within what we can see, there is little reason to think they are rare beyond it. Long before the first galaxies assembled, before gas cooled into stars, before light could travel freely through space, the universe passed through a phase that set the stage for everything that followed. This phase did not involve stars, planets, or any familiar structure. It involved space itself behaving in a way that no longer occurs today. To understand why the universe appears so large, so uniform, yet filled with structure, it becomes necessary to spend time with this early period, known as cosmic inflation, and with the tiny irregularities it left behind. At the very beginning, the universe was extraordinarily hot and dense. Matter and energy were packed together so tightly that individual particles could not exist independently in the way we think of them now. Space and time were already present, but conditions were extreme enough that many of the distinctions we rely on today lose their meaning. As the universe expanded and cooled, it passed through a series of transitions that shaped its later behavior. Cosmic inflation refers to a brief but dramatic episode during these earliest moments. For a tiny fraction of a second, space expanded at an exponential rate. Not just quickly, but astonishingly quickly. Regions of space that were once microscopic were stretched to astronomical scales. Distances that had been almost negligible became vast. This expansion was far more rapid than the expansion we observe today. It is important to be precise about what inflation does and does not mean. Inflation was not matter flying outward through space. It was space itself increasing in size at an extraordinary rate. Every point moved away from every other point, not because anything was pushing them, but because the geometry of space was changing. Why this happened remains one of the open questions in fundamental physics. Inflation is thought to have been driven by a field with unusual properties, one that produced a kind of negative pressure, causing space to expand rapidly. The exact nature of this field is still unknown. What matters for our story is not the detailed mechanism, but the consequences inflation had for the structure of the universe. One of the most important consequences of inflation is that it explains why the universe looks the way it does on large scales. When we observe the cosmos, we find that it is remarkably uniform. The temperature of the cosmic microwave background varies by only tiny amounts from one direction to another. The distribution of matter, when averaged over large enough distances, looks smooth and even. This uniformity is puzzling without inflation. In a universe without an early period of rapid expansion, distant regions would not have had time to interact or exchange information. They should look different, reflecting independent initial conditions. Inflation solves this by stretching a small causally connected region to enormous size. Before inflation, everything we can now observe was close together, able to come into equilibrium. Inflation then expanded that region so dramatically that it now encompasses the entire observable universe and more. But inflation does more than smooth things out. It also provides the seeds of structure. During inflation, quantum fluctuations, tiny random variations inherent to quantum fields, were stretched to macroscopic scales. What began as minute differences in energy density became the slight over- and under-densities that later grew into galaxies, clusters, and the cosmic web. These fluctuations were not added after the fact. They were built into the fabric of space as it expanded. Inflation froze them in place by stretching them faster than causal processes could smooth them out. When inflation ended and expansion slowed, these variations remained as imprints on the universe's initial conditions. Over billions of years, gravity amplified these small differences. Regions that were slightly denser than average attracted more matter. Regions that were slightly less dense became voids. The pattern of large-scale structure we see today traces back directly to these early fluctuations. This connection is not speculative. It is supported by precise measurements of the cosmic microwave background. The tiny temperature variations observed in that radiation correspond directly to density variations in the early universe. Their statistical properties match what inflation predicts with remarkable accuracy. James Webb does not observe inflation directly. Inflation occurred far too early for its effects to be seen in the form of light from that. What Webb does observe are the consequences of inflation playing out much later. The abundance, distribution, and maturity of early galaxies reflect the initial conditions inflation produced. When Webb shows that galaxies formed quickly and abundantly across wide regions of space, it reinforces the idea that the seeds for structure were already well distributed. Inflation naturally produces this outcome. By stretching fluctuations over enormous volumes, it ensures that many regions are primed for collapse once conditions allow. Another important implication of inflation is size. Inflation does not just make the observable universe large, it makes the total universe potentially enormous. The observable universe is only the portion of space from which light has reached us since the end of inflation and subsequent cosmic evolution. Inflation itself likely produced a region far larger than this observable patch. In many inflationary models, the universe beyond what we can see extends vastly farther, perhaps infinitely. The observable universe becomes a small sample of a much larger whole. This is not something James Webb can confirm directly, but its observations are consistent with a universe that does not run out of structure near the observational limits. The seeds laid down by inflation are also nearly scale invariant. This means that fluctuations have similar strength across a wide range of scales. This property allows structure to form on many sizes, from small galaxies to massive clusters. Webb's observations of early galaxies across different masses align with this expectation. There is no sudden cut-off where structure stops forming. Inflation also helps explain why early galaxies could form rapidly. The initial density variations provided by inflation meant that some regions started slightly ahead. In those regions, dark matter halos collapsed earlier, gas accumulated sooner, and star formation began quickly. Webb is likely observing the descendants of the highest peaks in the initial fluctuation field. This introduces an important subtlety. The galaxies Webb sees at extreme distances may not be representative of the average region at that time. They may represent the most overdense regions, the places where structure formed first. Even so, their abundance places constraints on how common such regions were, and thus on the overall size and nature of the universe. Inflation also predicts that the universe should be very close to geometrically flat. Measurements confirm this to high precision. A flat universe implies that the total extent of space is large compared to the observable portion. If space curves significantly on observable scales, we would see it in the cosmic microwave background and large-scale structure. We do not. Flatness does not require infinity, but it allows it. A flat universe can be finite or infinite, but if it is finite, its size must be much larger than what we can see. Inflation naturally drives the universe toward flatness by stretching any initial curvature to near invisibility. This geometric consequence ties directly into the feeling that the universe is larger than intuition suggests. Inflation does not merely explain early structure, it explains why the universe does not show obvious edges or curvature within our observational reach. There is also a temporal implication. Inflation compresses much of the universe's large-scale organization into its earliest moments. Once inflation ends, the broad pattern of structure is already laid down. Later evolution involves growth and refinement rather than fundamental rearrangement. This means that even at early times, large-scale coherence exists. When James Webb reveals that early galaxies are not isolated oddities but part of broader patterns, it is seeing this coherence in action. The universe did not slowly discover its structure over billions of years. Much of that structure was implicit from the start, encoded in the initial conditions inflation produced. It is worth noting that inflation is not without open questions. We do not yet know what caused it to begin or end. We do not know whether it happened once or is part of a larger process that continues in other regions. Some theories suggest that inflation may still be occurring elsewhere, producing a multiverse of expanding regions. These ideas remain speculative, but they arise naturally from the physics involved. What matters here is that inflation provides a framework in which a very large universe is not surprising. It provides a mechanism for creating vast regions of space that share similar properties. It provides seeds for structure that allow galaxies to form quickly and widely. And it provides geometric conditions that make the observable universe a small fraction of a much larger whole. James Webb's role is to test the downstream consequences of this framework. When its observations align with inflationary expectations, confidence in the broader picture increases. When tensions arise, they guide refinements rather than wholesale rejection. As you sit with this, it may help to notice how different this view of the universe is from everyday experience. Size is no longer something you estimate by looking outward. It is something inferred from patterns, statistics, and physical laws operating over immense spans of time and space. Inflation sets the initial scale, expansion stretches it further, and structure grows within it. The universe does not grow large slowly and then begin to form interesting things. It grows large first, very quickly, and then fills itself with structure according to rules laid down at the beginning. That sequence matters. It helps explain why, when we look far back with powerful instruments, we do not see a simple, empty universe, but one already busy with the work of becoming. When the universe is described as large, the word often brings to mind empty space, long distances, and the separation between bright islands of stars. But size in cosmology is not defined only by emptiness. It is defined by structure, by how matter organizes itself across expanding space. To understand why the universe did not remain smooth and diffuse, and why it built galaxies quickly across enormous regions, it becomes necessary to focus on something that does not emit light, does not reflect it, and does not absorb it in any ordinary way. Dark matter is not a minor ingredient added to the story later. It is one of the main reasons the universe looks as vast and populated as it does. In the early universe, shortly after it cooled enough for particles to exist independently, matter was divided into two broad categories. Ordinary matter, made of protons, neutrons, electrons, and later atoms, interacted readily with radiation. Dark matter, whatever its exact nature, did not. This difference shaped cosmic history from the beginning. Ordinary matter was tightly coupled to radiation in the early universe. photons scattered off electrons constantly, keeping matter hot and preventing it from collapsing easily under gravity. Pressure from radiation resisted compression. Dark matter, on the other hand, did not feel this pressure. It responded only to gravity. As a result, dark matter began clumping earlier than ordinary matter ever could. This early clumping was subtle at first. The density variations left behind by cosmic inflation were tiny, but gravity is persistent. Over time, dark matter responded to those variations by slowly drawing itself into denser regions. These regions grew into dark matter halos, invisible structures that defined where galaxies would later form. The importance of this process cannot be overstated. Without dark matter, ordinary matter alone would have struggled to form structure within the age of the universe. Expansion would have pulled matter apart faster than gravity could bring it together. Galaxies would have formed late, if at all, and the universe would look far emptier today. Dark matter provided gravitational wells deep enough to overcome expansion locally. Once a halo formed, ordinary matter could fall into it. Gas accumulated, cooled, and eventually formed stars. The halo did not shine, but it shaped everything that did. James Webb's observations of early galaxies highlight this role indirectly. When Webb detects massive galaxies at very high redshift, it implies the existence of massive dark matter halos at even earlier times. Stars do not appear without gravitational scaffolding. Seeing luminous structure early means the invisible structure must have formed earlier still. Dark matter halos also determine how galaxies grow. Their mass sets the depth of the gravitational potential. Deeper wells can hold onto gas more effectively, resisting the effects of stellar feedback that would otherwise blow gas away. In the early universe, where gas was plentiful, halos could be rapidly fed by inflows along cosmic filaments. These filaments are themselves dark matter dominated. Large-scale simulations of cosmic structure show that dark matter forms a web-like network spanning vast distances. Ordinary matter follows this network, flowing along filaments into nodes where halos grow largest. The result is a universe structured on enormous scales, with galaxies tracing patterns laid down by invisible mass. This web is not confined to a small region. It extends across the observable universe. Its scale reflects the initial conditions set by inflation and the properties of dark matter itself. When James Webb reveals early galaxies spread across large areas of the sky, it is revealing nodes in this web at an early stage of its development. Dark matter also affects how quickly structure forms. Because it does not radiate energy, it cannot lose kinetic energy through cooling the way gas does. This allows dark matter halos to form through gravitational collapse without dissipating energy. They settle into stable configurations that persist over cosmic time. Ordinary matter, by contrast, must cool to collapse further. It shocks, radiates, fragments, and forms stars. These processes take time. Dark matter's role is to provide a stable framework within which these slower processes can occur efficiently. The mass distribution of dark matter halos follows a predictable pattern. Small halos form first, then merge into larger ones. This hierarchical growth builds up structure from the bottom up. In the early universe, this process was rapid. Halos formed and merged frequently because the universe was smaller and denser. James Webb's detection of surprisingly massive early galaxies suggests that some halos grew very quickly, either through rapid accretion, frequent mergers, or both. This does not violate theoretical expectations, but it pushes them toward the upper end of what is plausible. It suggests that dark matter clustering was highly effective early on. There is also the question of how dark matter interacts with itself. Most models assume it interacts only gravitationally, but even slight self-interactions could alter how halos form and evolve. Webb's observations may eventually help constrain these properties by revealing how early galaxies are distributed and structured. Dark matter also influences the sizes of galaxies. The extent of a galaxy's dark matter halo determines how far its gravitational influence reaches. Larger halos correspond to larger galaxies and groups. When early galaxies appear already large, it implies their halos were already extensive, occupying significant volumes of space. This matters for our sense of cosmic size. If large halos formed early and often, then large regions of space were already gravitationally organized. The universe was not just expanding emptily, it was actively structuring itself across vast distances. Another important role of dark matter is in preserving information from the early universe. Because dark matter does not interact with radiation, it retains memory of the initial density fluctuations more faithfully than ordinary matter, which was smoothed by radiation pressure early on. This makes dark matter a kind of fossil record of inflationary conditions. The large-scale distribution of galaxies today reflects the distribution of dark matter halos. When James Webb observes early galaxies in unexpected abundance, it suggests that the underlying dark matter distribution supported that abundance. This feeds back into our understanding of how large the universe must be to accommodate such distribution statistically. There is also a subtle effect related to expansion. Dark matter halos decouple from expansion locally. Within a halo, gravity dominates, and the structure does not stretch with the universe. This creates islands of stability within an expanding sea. The larger and more numerous these islands are, the more structured the universe appears at any given time. In the early universe, these islands formed quickly in many places. This leads to a picture where, even as space expanded rapidly, structure kept pace locally. The universe did not dilute into emptiness. It maintained a high level of organization across growing distances. Dark matter's influence extends to reionization as well. The first stars and galaxies formed in dark matter halos. Their radiation reionized the intergalactic medium. The timing and uniformity of this process depend on how halos formed and clustered. Webb's observations of early galaxies help refine this timeline, indirectly informing dark matter models. It is also worth considering what dark matter does not do. It does not emit light. It does not obscure light directly. Its presence is inferred through its gravitational effects. This means that our understanding of it relies heavily on models and indirect measurements. Every new observational constraint matters. James Webb adds constraints by tightening the allowed range of early galaxy properties. If galaxies are more massive, more numerous, or more structured than expected, dark matter models must accommodate that. This may affect assumptions about the spectrum of initial fluctuations, the nature of dark matter particles, or the efficiency of halo growth. From a broader perspective, dark matter contributes to the universe's size by enabling structure to form efficiently across large volumes. A universe without dark matter would still expand, but it would be emptier, smoother, and less interesting. It would lack the dense networks that give meaning to distance. When we say the universe is large, we're not just counting kilometers or light years. We're describing a space filled with patterns that extend across those distances. Dark matter is the reason those patterns exist. James Webb does not see dark matter directly, but it sees its fingerprints everywhere. In the timing of galaxy formation, in the masses inferred from starlight, in the clustering of early galaxies. Each observation reinforces the idea that invisible structure played a dominant role from the beginning. When people hear the word edge, the mind immediately reaches for familiar images: a cliff, a wall, a boundary where something stops and something else begins. That instinct is deeply human, shaped by living in environments where space is finite and surfaces are tangible. But when cosmology uses language that sounds similar, it is pointing to something far less concrete. In relativistic cosmology, the idea of an edge does not describe a place you could travel to, nor a boundary you could cross. It describes a limit imposed by physics on what can be connected, observed, or influenced. Understanding this difference is essential for making sense of how large the universe may truly be. The first thing to set aside is the idea that the universe has an edge in the same way a continent has a coastline. There is no observational evidence for a physical boundary where space abruptly ends. General relativity, which governs our understanding of space-time on cosmic scales, does not require such an ending. In fact, most solutions to Einstein's equations describe universes without edges at all, even when they are finite in extent. This is one of the most counterintuitive features of relativistic cosmology. A universe can be finite yet unbounded. The classic analogy, imperfect but helpful, is the surface of a sphere. The surface has a finite area but no edge. You can travel indefinitely without encountering a boundary, yet you will never leave the surface. In 3 dimensions, similar geometries exist that allow space to be finite without having an edge. However, our universe appears to be very close to geometrically flat. This means that, on large scales, the rules of Euclidean geometry apply to a high degree of accuracy. Parallel lines do not converge or diverge noticeably. Triangles add up to very nearly 180 degrees. In such a geometry, space can be infinite, or it can be finite but extraordinarily large, wrapped in a way that is not easily detectable. In either case, there is no natural edge in the sense of a terminating surface. So where does the idea of an edge come from at all? It arises from observation, not from geometry. Specifically, it arises from the finite speed of light and the finite age of the universe. These 2 facts together create horizons. Horizons are limits on what can be observed or influenced, not because space ends, but because information has not had time to travel. The most familiar of these is the particle horizon, which defines the boundary of the observable universe. It marks the greatest distance from which light has reached us since the universe became transparent. Beyond this horizon, there may be galaxies, matter and structure, but their light has not arrived yet. They are not observable, not because they are hidden behind something, but because the universe has not existed long enough for information to travel from there to here. This horizon behaves like an edge in a practical sense. It defines the limit of what we can see, but it is not a physical boundary. If you could instantly relocate to a distant galaxy, your observable universe would shift with you. You would see regions that are currently beyond our horizon, and you would lose sight of some regions we can currently observe. The horizon is tied to the observer, not to space itself. Relativity makes this observer dependence unavoidable. There is no universal present moment that slices the universe into a single shared now. Different observers moving relative to each other define simultaneity differently. As a result, the notion of a single cosmic edge that exists at a specific location for everyone does not make sense within relativistic spacetime. Another important horizon is the event horizon, which arises because the expansion of the universe is accelerating. This horizon defines a boundary beyond which events that occur now will never influence us, even in principle. Light emitted beyond this horizon today will never reach us, no matter how long we wait, because space between us and the source expands too quickly. This event horizon behaves even more strongly like an edge, but again, it is not a physical wall, it is a causal limit. It marks the boundary of future connectivity, not present existence. Regions beyond it are real if the universe extends that far, but they are causally disconnected from us going forward. In relativistic cosmology, causality replaces containment. The universe is not divided by walls or borders. It is divided by which regions can exchange information. Edges are not places. They are relationships between events in space-time. James Webb's observations interact with this idea in a subtle way. Webb does not push past any horizon. It cannot see beyond the particle horizon, and it cannot access regions beyond the event horizon. What it does is fill the observable universe more densely than before. It shows that near the observational limits, there is more structure than expected. This makes the horizon feel less like the edge of a sparse frontier and more like the boundary of a crowded city whose outskirts fade gradually into darkness. This change in perception matters. When the observable universe appeared sparsely populated at great distances, it was easier to imagine that perhaps we were seeing close to the end of things. When that same region turns out to be rich with galaxies, the idea of an edge becomes less compelling. It feels less like a boundary and more like an arbitrary cutoff imposed by our position in time. Relativistic cosmology also allows for the possibility that the universe is infinite. In an infinite universe, there is no edge anywhere, not even in principle. Horizons still exist, but they limit observation, not existence. In such a universe, the observable universe is an infinitesimally small patch of an unending whole. Even if the universe is finite, its size could be so large that its curvature is undetectable within the observable region. In that case, space might wrap around on scales far larger than we can see. Again, no edge would appear within any region accessible to observation. The absence of an edge has important consequences for how we interpret cosmological data. It means that we cannot infer the total size of the universe by looking for boundaries. We must instead rely on indirect reasoning, using geometry, statistics, and physical models to constrain what lies beyond observation. For example, the uniformity of the cosmic microwave background across the sky suggests that the universe extends well beyond the observable horizon. Inflation provides a mechanism for this, but the observation itself already points toward a universe larger than what we can see. James Webb's observations add another layer, showing that structure formation was widespread near the observational limits, further supporting the idea of a universe that does not taper off quickly beyond our reach. There is also a philosophical adjustment required here. In everyday language, size is often defined by edges. A room has walls, a field has fences, a map has borders. Without edges, size feels undefined. Relativistic cosmology asks us to redefine size in terms of scale and extent rather than containment. The universe can be large not because it has faraway edges, but because distances between points are immense. It can be larger still because those distances continue beyond what we can measure. The absence of an edge does not make size meaningless. It makes it harder to grasp intuitively. Another subtlety comes from space-time diagrams. In relativity, events are plotted in a combined space and time framework. Horizons appear as slanted lines, not as vertical boundaries. They separate regions that can influence each other from those that cannot. This reinforces the idea that edges in cosmology are temporal as much as spatial. When we ask where the edge of the universe is, we're often really asking when the universe becomes inaccessible to us. The answer depends on the entire expansion history, the behavior of dark energy, and the future evolution of space-time. It is not a single location that can be pointed to. James Webb's role in this context is to remind us how misleading edge-based thinking can be. By revealing complexity and structure at distances once thought to be close to the limit of formation, it shows that the universe does not thin out in a simple way as we approach observational horizons. The cutoff is observational, not physical. There is also an emotional dimension to the idea of an edge. Humans often find comfort in boundaries. An edge suggests completion. It suggests that everything can be accounted for. Relativistic cosmology denies us that comfort. It replaces it with horizons that move, depend on perspective, and change over time. As the universe expands, the particle horizon grows, allowing us to see more. At the same time, the event horizon restricts what will ever be seen. These two horizons move in opposite conceptual directions. One opens the past, the other closes the future. Neither corresponds to an edge in space. This dynamic picture fits naturally with what James Webb shows us. The universe is not a static container with a size waiting to be measured. It is a process. Its apparent size depends on when and how we look. Each improvement in observation reshapes our understanding of what fills the observable region, even as the limits themselves remain defined by fundamental physics. So when we talk about the universe being larger than we thought, we are not discovering a new edge farther away. We are discovering that within the limits imposed by relativity, there is more than expected. More structure, more mass, more early activity. That abundance makes it increasingly unlikely that the observable universe is anywhere near the full extent of what exists. The idea of an edge dissolves into something quieter and more complex. There are limits, but they are limits of connection, not of existence. They arise from time, not from walls. And as long as the universe continues to expand, those limits will continue to define what we can know, without ever marking where the universe itself ends. Once the idea of an edge dissolves into something less concrete, another framework quietly takes its place. In relativistic cosmology, what truly defines the limits of our knowledge is not distance alone, but causality. The universe is structured not just by where things are, but by which events can influence which other events. This is where horizons and light cones become essential, not as abstract mathematical constructs, but as practical boundaries on what can ever be observed, measured, or affected. To begin, it helps to focus on something very simple and very strict. Information cannot travel faster than light. This is not a technological limitation. It is built into the structure of space-time itself. No signal, no force, no causal influence can outrun light in a vacuum. This single rule quietly governs everything from particle interactions to the large-scale shape of the observable universe. Every event in space-time can be thought of as having a sphere of influence. That sphere expands outward at the speed of light as time passes. Inside that sphere are events that can, in principle, be affected by the original event. Outside it are events that cannot. This expanding region is represented in space-time diagrams as a light cone. A light cone has two parts. The future light cone contains all events that can be influenced by a given event. The past light cone contains all events that could have influenced it. Anything outside both cones is causally disconnected. No information can travel between those regions without violating the speed of light. In everyday life, light cones are invisible and irrelevant. The distances are small and the timescales are short. Everything around us shares causal contact. In cosmology, light cones define everything we can possibly know. Your past light cone defines the observable universe. Every galaxy you see, every photon detected by James Webb or any other telescope, lies within that cone. If light from an event has not had time to reach you, that event lies outside your past light cone. It is not hidden behind something, it is not obscured, it is causally inaccessible. This immediately reframes the idea of what we can never see. It is not about insufficient power or better instruments. It is about whether light has had time to arrive. The particle horizon marks the boundary of the past light cone at the current moment. It defines the maximum distance from which light emitted since the universe became transparent could have reached us. Beyond it there may be galaxies, stars and structure, but no information from them has arrived yet. As time passes, this horizon grows. Light from slightly farther regions reaches us. The observable universe expands, but it does so asymptotically. There is a limit to how much information will ever arrive, because expansion itself interferes. This brings us to the event horizon. Unlike the particle horizon, which looks backward in time, the event horizon looks forward. It defines the boundary beyond which events occurring now will never be able to influence us, even in principle. Light emitted today from beyond this horizon will never reach us, no matter how long the universe exists. The existence of a cosmic event horizon depends on the expansion history of the universe. Because expansion is accelerating, driven by dark energy, distant regions are being carried away from us faster and faster. Eventually the space between us and those regions expands so quickly that light cannot make headway against it. This means there are parts of the universe that are already permanently inaccessible. They exist now, but they are causally disconnected from our future. We will never receive information from them. No telescope, no matter how advanced, can change this. James Webb operates entirely within these causal limits. It cannot see beyond the particle horizon, and it cannot reveal regions beyond the event horizon. What it can do is show us how much structure exists near the edge of the past-like cone, where observational limits are tightest. What Webb has revealed is that this region is not empty or primitive. It is busy, structured, and active. That matters because it changes how we think about what lies beyond the horizon. If regions close to the observational limit are already rich with galaxies, it becomes increasingly implausible that structure suddenly stops just beyond it. Still, plausibility is not observability. Horizons remain absolute. No amount of inference can replace direct causal contact. Light cones also explain why there is no universal now in cosmology. Different observers have different past and future light cones. Events that are simultaneous for one observer may not be simultaneous for another moving relative to them. This destroys the idea of a shared cosmic present moment. In practical terms, this means the universe does not exist as a single snapshot that we are gradually uncovering. It exists as a network of events connected by causal relationships. What we observe is always a slice through that network defined by our own position in space-time. This has deep implications for size. When we say the universe is large, we are not describing a static object with known dimensions. We are describing the extent of causal connectivity. The observable universe is large because our past-like cone intersects a vast region of space-time. The total universe may be far larger, but size beyond our light cone is not something we can measure directly. Another important feature of light cones is that they tilt in expanding space. In a static universe, light cones would be symmetric and straightforward. In an expanding universe, their shape changes over time. Early in cosmic history, light cones were narrower. Later, they widened. Acceleration changes their structure again, limiting future connectivity. This dynamic behavior is why some galaxies we can see today will eventually disappear from view. As expansion accelerates, light emitted by distant galaxies will be stretched to longer wavelengths, eventually beyond detectability. Those galaxies will slip beyond the event horizon. Future observers may see a much smaller observable universe than we do now. James Webb's observations occur during a relatively privileged era. We live at a time when the universe is old enough for complex structure to exist, but young enough that much of it is still observable. This window will not last forever. This adds a quiet urgency to cosmology, not urgency in the emotional sense, but in the sense that observation is time-dependent. What we can see now is not what observers will see in the distant future. The universe's apparent size will shrink, even if its actual size continues to grow. Horizons also complicate the interpretation of completeness. Even if the universe is infinite, we will never observe more than a finite portion. That portion is bounded by light cones. Any claims about the universe as a whole must rely on extrapolation from what lies within our horizon. James Webb improves that extrapolation by making the observable region more representative. When the edge of our past light cone turns out to be rich rather than sparse, extrapolation becomes more reliable. The universe looks more uniform across scales, supporting the idea that the observable region is not unusual. But there are still things we can never see. Regions beyond the particle horizon, events beyond the event horizon, early moments before the universe became transparent to light. Physics allows us to model these indirectly, but not observe them directly. This is not a failure. It is a feature of relativistic space-time. Knowledge is bounded by causality. Understanding this helps prevent a common misunderstanding. When new telescopes extend our reach, they do not push the universe's boundaries outward in a physical sense. They refine our view within fixed causal limits. Each improvement fills in more detail, not more universe. James Webb's contribution is to show us that within those limits, there is more than we expected. More galaxies, more mass, more early structure. That abundance reshapes how we think about the unseen regions beyond our light cone, even though it does not reveal them directly. Light cones also remind us that time itself is asymmetric. We can see the past but not the future. We can infer what lies ahead only through models. Horizons enforce this asymmetry. They define what can be known, not just now, but ever. The universe begins to feel less like a place and more like a process constrained by speed, expansion, and causality. Horizons are not walls, they are the shape of information flow. At first glance, the idea sounds like a contradiction. How can something be bigger than its own age would seem to allow? If the universe is about 13.8 billion years old, and nothing can travel faster than light, then it feels reasonable to assume that the universe should be about 13.8 billion light-years across. That expectation is neat, intuitive, and completely wrong in a relativistic, expanding universe. Letting go of that intuition is one of the quiet turning points in understanding cosmic size, and it rests on separating three ideas that everyday thinking tends to bundle together: time, motion, and distance. To begin, it helps to acknowledge where the intuition comes from. In ordinary experience, distance grows because things move. A car covers more ground the longer it drives. A person walking away from you becomes farther away as time passes. If you know how fast something moves and how long it has been moving, you can estimate how far it has gone. This logic works because the space between you and the object is static. It does not stretch. It does not shrink. It simply sits there while things move through it. Cosmology breaks that assumption at the most fundamental level. On the larger scales, space itself is not static. It expands. This single fact severs the simple link between age and size. When we say the universe is 13.8 billion years old, we're referring to the time since the hot, dense early state from which it expanded. When we say light travels at a finite speed, we are referring to motion through space. The mistake is to assume that space itself has remained the same size during that time. It has not. It has been stretching continuously, and sometimes very rapidly. Because of this stretching, light does not simply cross a fixed distance on its way to us. The distance itself changes while the light is in transit. The photon is not running across a stationary track. The track is being pulled out from under it as it moves. This is why the radius of the observable universe is not 13.8 billion light-years, but about 46 billion light-years. Light from the most distant regions we can observe has been travelling for 13.8 billion years, but during that time the space it travelled through expanded significantly. The source of that light is now far farther away than it was when the journey began. This does not violate the speed of light. At no point did the photon exceed that speed locally. Instead, the geometry it travelled through changed. The key idea here is that distance in cosmology is not something that accumulates only through motion. It accumulates through expansion as well, and expansion has no upper speed limit in the way motion through space does. Space can stretch so that two distant points separate faster than light without breaking any physical laws, because nothing is locally outrunning a photon. This immediately allows the universe to be much larger than its age might suggest. Another way to approach this is to focus on what the age of the universe actually measures. The age is a time coordinate. It tells us how much time has elapsed since a particular physical condition existed everywhere, namely the early hot, dense state. It does not tell us how much space exists now. Space is not conserved. It is not a fixed quantity that simply gets filled over time. It is dynamic. This becomes clearer when you consider that the universe did not start at a point in space. The Big Bang was not an explosion at a location. It was a state where space itself was extremely compact everywhere. Every region was close to every other region, because space itself was small. As time progressed, space expanded. Distances grew not because matter flew outward into emptiness, but because the metric defining distance changed. Because of this, asking how big the universe was at the beginning is a misleading question. The universe did not have a size in the usual sense. It had a scale defined by the scale factor in cosmology, and that scale factor increased with time. Size is something that emerges as expansion proceeds. This also means that there is no requirement for the current size of the universe to be proportional to its age. The relationship depends on how the expansion rate changed over time. Early in cosmic history, expansion was extremely rapid. During inflation, space expanded exponentially for a brief moment. Regions that were once microscopic were stretched to astronomical scales almost instantly. This alone allows the universe to become enormous without requiring much time at all. After inflation ended, expansion slowed. But it did not stop. It transitioned through different regimes. When radiation dominated, expansion behaved one way. When matter dominated, it behaved another way. More recently, dark energy has caused expansion to accelerate again. Each of these phases contributed differently to how much space exists now. Time passed steadily, but space grew unevenly. This is why two universes with the same age could have very different sizes if their expansion histories differed. Age alone does not fix size. Expansion history does. When James Webb shows us galaxies that existed very early and are now tens of billions of light years away, it is not revealing a paradox. It is revealing the cumulative effect of expansion layered on top of light travel time. Those galaxies did not have to go that far, space carried them. Another subtle point is that the observable universe is not the same thing as the universe itself. The observable universe is limited by how far light has had time to travel to us. The universe beyond that may be far larger, potentially infinite. The age of the universe places no constraint on that total size. To see why, imagine a universe that is infinite in extent from the very beginning. At early times, it is still infinite, just denser and hotter. Expansion increases distances everywhere, but infinity remains infinity. The age of the universe tells you nothing about its total size in that case. Even if the universe is finite, it could be so large that only a small region has ever been observable. Inflation strongly suggests this possibility. By stretching space enormously early on, inflation can produce a universe whose total extent dwarfs the observable portion. In this context, the observable universe is not a measure of total size, it is a measure of causal reach. It tells us how far information has travelled, not how far space extends. Another way to see this is through comoving coordinates. In comoving terms, distances between points moving with the cosmic expansion remain fixed. These coordinates stretch with the universe. In comoving space, the observable universe has a fixed radius. In proper distance, that radius grows with time. This distinction reinforces the idea that size is frame-dependent in cosmology. The same region of space can have different sizes depending on how and when you measure it. Time does not uniquely determine distance. Redshift further complicates the intuition. Redshift is often described as a measure of distance, but it is really a measure of expansion. Two objects with the same light travel time can have different redshifts if the expansion history along their lines of sight differs. This means that even time and expansion are not linked in a simple one-to-one way. James Webb's measurements emphasize this complexity. By observing high redshift galaxies with unexpectedly large masses and high star formation rates, it shows that large-scale structure emerged early across wide regions. Those regions are now separated by enormous distances, much larger than the age of the universe would naively suggest. This does not mean the universe cheated time. It means time was not the limiting factor. There is also a psychological element to the confusion. Human intuition is shaped by living inside systems where space is static and time flows independently. In cosmology, space and time are intertwined. The metric that defines distance evolves with time. You cannot hold one fixed while varying the other. Relativity enforces this coupling. In general relativity, space-time is a single entity. Expansion is a property of space-time itself. Distance is not an independent backdrop. It is part of the dynamic geometry. Once this is accepted, the idea that the universe can be larger than its age stops feeling strange. It becomes expected. James Webb does not directly measure the total size of the universe. No instrument can. What it does is show us that within the portion we can see, space was already being filled efficiently with structure very early on. That efficiency fits naturally into a picture where the universe had ample room to grow into. If the universe were barely larger than the observable region, or if it had tight global constraints on its size, early widespread structure would be harder to accommodate without fine-tuning. A large universe makes such observations less surprising. It becomes easier to let go of the instinct to equate age with size. The universe is not a road being paved outward at a fixed speed. It is a fabric being stretched, sometimes gently, sometimes violently, over time. Age tells us how long that stretching has been happening. It does not tell us how much fabric there is. When new observations arrive that do not sit comfortably inside existing expectations, physics does not respond by throwing everything away. It responds by adjusting, refining, and sometimes stretching the models that already exist. Cosmology, in particular, is built on frameworks designed to absorb new information without collapsing. The arrival of data from James Webb did not overturn modern cosmology, but it did apply pressure in specific places, and pressure is often where understanding improves. Before James Webb, cosmological models were already remarkably successful. They described an expanding universe governed by general relativity, filled with ordinary matter, and dark energy. They reproduced the large-scale distribution of galaxies, the detailed structure of the cosmic microwave background, and the overall timeline of cosmic evolution with impressive precision. Within this framework, early galaxies were expected to exist, but in limited numbers and with relatively modest masses. These expectations were not guesses. They were derived from simulations that combined gravity, hydrodynamics, radiation, and feedback processes. Such simulations begin with initial conditions informed by inflation and the cosmic microwave background, then evolve forward in time. The resulting virtual universes could be compared statistically to observations. For many years, the match was good enough to inspire confidence. James Webb did not break that match outright. What it did was reveal that some aspects of early galaxy formation appear to sit near the extreme edge of what those simulations predicted. Galaxies at very high redshift appeared more numerous, more massive, and in some cases more structured than anticipated. Individually, each observation could be explained. Collectively, they suggested that something about early structure formation might be more efficient than previously assumed. This is where model revision begins, not with panic, but with careful questioning. One of the first areas under scrutiny is star formation efficiency. In many simulations, assumptions are made about how quickly gas turns into stars. These assumptions are based on observations of nearby galaxies and on theoretical considerations about cooling, turbulence, and feedback. Early galaxies, however, existed under very different conditions. Gas densities were higher, metallicity was lower, radiation fields were different. It is plausible that star formation proceeded more efficiently in the early universe than in later epochs. If star formation efficiency is increased in models at high redshift, galaxies become brighter and more massive more quickly. This alone can bring simulations closer to Webb's observations without changing the underlying cosmological framework. Another area of adjustment involves feedback. Feedback from stars and black holes injects energy into surrounding gas, regulating growth. In many models, feedback is tuned to reproduce present-day galaxy populations. If feedback was less effective in the earliest galaxies, gas could accumulate and form stars rapidly, before self-regulation became dominant. Slight changes in feedback prescriptions can have large effects on early growth. Dark matter halo growth rates are also being revisited. The formation and merger rates of halos depend on the initial fluctuation spectrum and on the details of gravitational collapse. If the highest density peaks collapse slightly earlier or more rapidly than assumed, early massive galaxies become more common. This does not require exotic physics. It can arise from statistical variations amplified by nonlinear growth. There is also the question of how masses are inferred observationally. James Webb measures light, not mass. Converting light into mass requires assumptions about stellar populations, initial mass functions, dust content, and star formation histories. Small changes in these assumptions can shift inferred masses significantly. Ongoing work aims to refine these conversions using Webb's improved spectral data. Some early tension between models and observations has already eased as these refinements are applied. Initial claims of extremely massive early galaxies have been moderated as analyses improved. This is a normal part of scientific iteration. Early data provoke bold interpretations which are then refined through careful cross-checking. However, even with these adjustments, Webb's data suggests that the early universe was highly productive. This reinforces the need to ensure that models capture the full range of plausible early behaviors rather than being anchored too strongly to later epochs. Importantly, none of these revisions require changing the basic cosmological parameters that define the universe's expansion, geometry, or age. The values associated with dark energy density, dark matter density, and overall curvature remain consistent with other independent measurements. James Webb does not challenge the foundation. It challenges the details of how structure fills that foundation. This distinction matters when discussing size. The models that describe an expanding universe with a finite observable horizon and potentially vast unobservable regions remain intact. If anything, Webb's observations make large-scale assumptions more comfortable. A universe that supports rapid and widespread early structure formation fits naturally into a picture where space extends far beyond what we can see. There is also a broader methodological shift happening. Models are increasingly designed to explore a wider parameter space rather than converging tightly on a single, best scenario. This reflects recognition that early cosmic conditions may have allowed for more diversity in outcomes than later ones. Webb's data encourage this openness. Another area of revision involves the timing of reionization. The abundance of early galaxies suggests that the universe may have been reionized earlier or more rapidly than some models predicted. This has implications for how ultraviolet radiation propagated through space and how gas cooled and collapsed. Adjusting reionization histories feeds back into galaxy formation models, affecting star formation and visibility. There is also renewed interest in alternative dark matter models. While standard cold dark matter remains consistent with most observations, subtle differences in small-scale structure could influence early galaxy formation. Webb's data provide new constraints that may help distinguish between these possibilities. This does not mean dark matter needs to be redefined, but that its properties may be probed more finely. Throughout this process, it is important to recognize what is not happening. There is no crisis. Cosmology is not broken. The models are not being discarded. They are being tuned, stress-tested, and improved. This is exactly how a mature scientific field evolves when new, higher-quality data arrive. James Webb's role is catalytic. By pushing observations into a regime where models had less empirical guidance, it exposes assumptions that were previously safe. Some of those assumptions hold. Others require modification. Either outcome increases understanding. There is also a shift in confidence regarding extrapolation beyond the observable universe. Cosmological models rely on the assumption that the observable region is representative. Webb's findings support this assumption by showing that structure formation behaves robustly, even near observational limits. This strengthens the case for using models to infer properties of the universe beyond direct observation. As models adapt, the picture that emerges is not of a universe that barely fits within its age, but of one that comfortably accommodates vast distances, rapid early growth, and rich structure. Size becomes something that emerges naturally from the interplay of expansion, gravity, and initial conditions, rather than something that must be carefully constrained to avoid contradictions. This process of revision is ongoing. Future observations from James Webb and other instruments will continue to test and refine models. Some current interpretations will change, others will solidify. What remains consistent is the framework that allows such changes to happen without destabilizing the whole. As this settles, attention begins to shift away from whether models can survive Webb's data, and toward what new questions those models can now address. If early structure formation was more efficient than expected, what does that imply about the earliest phases of cosmic history? How does this efficiency propagate through later epochs? And what does it tell us about the full extent of the universe that supports such behavior? Even after decades of careful observation, precise measurement, and increasingly sophisticated models, some of the most basic questions about the universe remain unsettled. Not because physics has failed, but because the universe itself does not offer simple answers. When we talk about size, scale, and curvature, we're not talking about a single unknown waiting to be filled in. We're talking about a network of related uncertainties, each tied to limits of observation, to the behavior of space-time, and to the assumptions we are forced to make when direct measurement is impossible. At a glance, modern cosmology appears confident. We can quote the age of the universe to within a small margin. We can describe its expansion history. We can measure the distribution of galaxies across enormous distances. We can state that space is very close to flat, and yet beneath that confidence lies a set of open questions that have not narrowed with time as much as one might expect. In some cases, they have become sharper. The question of size is the most obvious. How big is the universe really? The honest answer is that we do not know, and may never know in a direct sense. We know the size of the observable universe. We know the physics that governs expansion. We know how curvature behaves locally. But the total extent of space lies beyond observation, shielded by horizons that no improvement in technology can cross. This forces cosmology into an unusual position. It must describe something potentially infinite using finite data. It must infer global properties from local measurements, and it must do so while acknowledging that those inferences depend on assumptions about uniformity and symmetry. One of those assumptions is the cosmological principle, the idea that on sufficiently large scales the universe is homogeneous and isotropic. In plain terms, it looks roughly the same everywhere and in every direction when averaged over large distances. This principle is supported by observations within the observable universe. The cosmic microwave background is remarkably uniform. Large-scale galaxy surveys show no preferred direction or location, but the cosmological principle cannot be tested beyond the observable universe. It is an assumption extended beyond data. It is a reasonable assumption, but it is still an assumption. If the universe were significantly different beyond our horizon, we would have no direct way of knowing. This uncertainty feeds directly into the question of size. If the universe is homogeneous everywhere, then the observable region is a fair sample, and its properties can be extrapolated outward. If it is not, then the total size and structure could differ dramatically from what we infer. Closely tied to size is scale. Scale is not just about how big the universe is, but about how its properties change with distance. Does structure repeat? Does it smooth out? Does curvature emerge at very large scales? Observationally, the universe appears smooth beyond a certain scale, roughly a few 100 million light-years. Below that scale, matter is clumpy. Galaxies form groups, clusters, filaments, and voids. Above that scale, those clumps average out. This transition supports the idea that the universe has a characteristic scale of structure. But does that smoothness persist indefinitely? Or is it a local feature of the observable region? Again, the answer depends on extrapolation. James Webb's observations reinforce the idea that structure formation behaves consistently even near the observational limits, but they do not eliminate the possibility of surprises beyond them. Curvature adds another layer of uncertainty. general relativity allows space to be positively curved, negatively curved, or flat. Positive curvature corresponds to a closed universe, finite in volume. Negative curvature corresponds to an open universe, infinite in extent. Flat curvature sits at the boundary, allowing both finite and infinite possibilities depending on topology. Measurements of the cosmic microwave background indicate that the universe is very close to flat. But very close is not the same as exactly. Even tiny curvature could imply a finite universe with a size far larger than the observable region. Conversely, exact flatness could imply infinite extent, or a finite but topologically complex space. Topology is one of the least constrained aspects of cosmology. Space could be connected in ways that repeat patterns at scales larger than we can see. Searches for such patterns have not found clear evidence, but absence of evidence is not evidence of absence when observational reach is limited. James Webb does not measure curvature directly, its role is indirect. By refining measurements of structure formation, mass distribution, and early galaxy abundance, it tightens constraints on models that also predict curvature. As those models converge, they may favor certain geometries over others, but the door remains open. Another open question concerns the scale of inflation. Inflation explains why the observable universe is large, uniform, and flat. But inflation itself does not have a fixed scale. Depending on the model, inflation could have expanded space by a modest factor, or by an unimaginably large one. The observable universe could be a tiny patch of an enormous inflationary region. Some models even suggest that inflation may still be occurring elsewhere, producing an endlessly growing multiverse of expanding regions. In such scenarios, size loses its usual meaning entirely. The universe becomes not a single object, but a process that generates space continuously. These ideas remain speculative, but they arise naturally from attempts to connect inflation to fundamental physics. James Webb cannot confirm or deny them, but its observations of early structure are consistent with inflationary predictions that favor large-scale uniformity and extensive space. Another unresolved issue is the nature of dark energy. Dark energy drives the accelerated expansion of the universe, influencing horizons, causal structure, and the future size of the observable region. But its physical origin is unknown. It could be a constant property of space. It could evolve over time. It could be a sign that our understanding of gravity is incomplete. Different dark energy models predict different expansion histories. Those histories affect how large the universe becomes over time and how horizons behave. Current observations favor a simple model with constant dark energy density, but uncertainties remain. Even small deviations could have large consequences over cosmic timescales. There is also the question of whether the laws of physics themselves are truly uniform across all of space. We assume that physical constants are the same everywhere. So far, observations support this within the observable universe, but again, beyond that region, direct tests are impossible. If physical laws varied across space, size would become a more complicated concept. Regions with different physics could expand differently, form structure differently, and exhibit different curvature. The universe could be heterogeneous on scales far beyond observation. James Webb's data strengthen confidence in uniformity within the observable region by showing consistent behavior of galaxies across large distances and times. That consistency makes extreme variation less likely, but it cannot rule it out entirely. Another subtle question involves scale relativity. Some approaches to quantum gravity suggest that space-time itself may behave differently at different scales. Distance might not be a smooth, continuous quantity at the smallest scales. While these ideas are far removed from Webb's observations, they influence how physicists think about size at a fundamental level. If space-time has a minimum scale, or if geometry emerges from more basic structures, then size becomes an emergent property rather than a fundamental one. The universe could be large not because it contains many units of space, but because space itself arises from deeper processes that allow extensive structure. All of these open questions share a common feature. They are not questions that can be answered by simply looking farther or building a bigger telescope. They are questions about inference, interpretation, and the limits imposed by causality and expansion. James Webb pushes those limits by filling in the observable universe more completely than before. It reduces uncertainty within the region we can see. That reduction sharpens questions about the region we cannot. When the observable universe looked sparse and underdeveloped near its limits, it was easier to imagine that perhaps we were approaching the full extent of meaningful structure. As it looks richer and more complex, the idea that we are seeing only a fraction becomes harder to ignore. This does not mean the universe must be infinite. It means that its size, whatever it is not constrained by our age or our observational reach in a simple way. It could be finite yet unimaginably large. It could be infinite. Both possibilities remain open. Scale, too, resists closure. There may be no largest meaningful scale, only scales beyond which our models remain untested. Curvature may be exactly zero, or it may be non-zero but too small to detect locally. Each option carries different implications, none of which can yet be ruled out. What James Webb contributes to this landscape is not an answer, but a narrowing of ignorance. It shows that the universe does not behave timidly near the edges of what we can see. It behaves robustly. That robustness supports models where size is not tightly constrained, where space extends generously, and where early structure formation is not a rare fluke. As these ideas settle, it becomes clear that cosmology is not moving toward a final measurement of size, but toward a deeper understanding of why size itself is such a difficult concept. The universe does not present itself as an object to be measured end to end. It presents itself as a space-time whose properties unfold over time, shaped by expansion, gravity, and initial conditions. The remaining questions about size, scale, and curvature are not signs of failure. They are signs that cosmology has reached the boundary where observation meets principle. Beyond that boundary, reasoning must take over, guided by consistency, simplicity, and the behavior of the part we can see. As everything we've explored slowly settles, it becomes clear that none of these ideas were ever pointing toward a finish line. They were pointing toward motion, expansion that never quite pauses, structure that never fully completes itself, questions that soften rather than close. When we talk about the universe being larger than we thought, or older in its complexity than expected, we're not uncovering a final picture. We're recognizing that the picture is still being drawn. James Webb did not show us a universe that suddenly changed. It showed us a universe that had always been in the process of becoming, one whose scale was never meant to be grasped all at once. What changed was our access, our ability to listen to older light, our patience in interpreting what that light carries, and our willingness to accept that size, in cosmology, is not something you arrive at. It is something you infer while standing inside it. Throughout this journey, one theme has quietly repeated itself. The universe does not present itself as a finished object. It presents itself as an unfolding system governed by rules that allow vastness to emerge naturally. Expansion stretches space. Gravity shapes matter. Light carries information across time. None of these processes stop simply because we have named them. They continue whether or not we are watching. The observable universe, large as it is not a container we are filling with knowledge piece by piece. It is a moving horizon defined by time and causality. As time passes, some regions enter that horizon while others slip beyond future reach. The universe we can see today is not the same universe that could have been seen billions of years ago, and it will not be the same universe visible billions of years from now. James Webb arrived during a particular moment in that unfolding, a moment when early galaxies are still visible, a moment when expansion has not yet hidden most of the cosmos from view, a moment when the universe is old enough to have complexity, but young enough to still be generous with its light. That timing matters. When Webb shows us galaxies that formed early and across wide regions, it is not merely filling in gaps. It is reminding us that the universe was already active long before familiar structures existed. Space did not wait to grow large before becoming interesting. It grew large while becoming interesting. This realization subtly shifts perspective. It moves us away from thinking of ourselves as late arrivals at the edge of a finished story. Instead, we are participants in an ongoing process. The universe is not something that reached its full size and then settled into quiet repetition. It is something that continues to expand, reorganize, and evolve. Even the idea of how big the universe is begins to feel less urgent when framed this way. Size becomes less about totals and more about behavior. How space stretches, how structure fills it, how information flows within it. The universe can be unimaginably large and still incomplete in its unfolding. The physics we've followed, from inflation to dark matter to expansion and horizons, does not describe a static backdrop. It describes a system that changes its own scale. Distance itself is not fixed. Geometry evolves. What counts as far depends on when you ask the question. This has an unexpected calming effect when you sit with it. If the universe is not finished, then neither is our understanding of it meant to be. Uncertainty is not a flaw in the picture. It is part of the picture. James Webb sharpened that uncertainty rather than eliminating it. By revealing richness where sparsity was expected, it made the unknown feel larger, not smaller. But it also made it feel more coherent. The universe behaves consistently, even when it surprises us. The same physical rules apply across enormous distances and times. That consistency is what allows inference at all. There is also something quietly grounding about realizing that no single observer ever has access to the whole. Every perspective is partial. Every observation is bounded by light cones and horizons. Knowledge itself is local, even when it speaks about the cosmos as a whole. From inside the universe, size is always inferred, never surveyed. There is no outside vantage point, no place to stand and look back at everything. Even imagining such a position violates the very structure of space-time we've been discussing. And yet, from inside this limitation, remarkable coherence emerges. We can trace expansion histories. We can map structure across billions of light years. We can reconstruct conditions that existed when the universe was only a tiny fraction of its current age. That is not trivial. It is a quiet testament to how deeply the universe allows itself to be understood, even while withholding final answers. As you rest with these ideas, it may help to notice how different this is from everyday thinking. In daily life, completion is reassuring. Projects end. Questions are answered. Spaces have edges. Cosmology offers a different rhythm. One where understanding deepens without closure. One where boundaries are informational rather than physical. One where size is not something you reach, but something that keeps revealing new context. Existing inside such a universe subtly changes the meaning of scale. Human life is small in duration and extent, but it is not disconnected. The same expansion that carries galaxies apart carries time forward here. The same laws that govern the largest structures govern the smallest interactions. There is continuity, even across vast differences in scale. James Webb's images often evoke awe, but the deeper effect is quieter. They show that the universe did not rush to simplicity at its beginnings. It embraced complexity early and often. That complexity did not require special circumstances. It emerged naturally from the way space, matter, and time interact. This suggests that largeness is not an accident. It is not excess. It is the natural outcome of a universe whose rules allow space to grow and structure to form efficiently. A universe like that does not need to stop at minimal size. It does not need to taper off neatly at the edges of observation. And so, when we say the universe is still unfolding, we mean that literally. Expansion continues. Structure continues to evolve. Horizons shift. Some regions drift beyond future contact while others remain visible for now. The story does not conclude with our observations. They simply occupy one frame in a much longer sequence. As this exploration comes to rest, there is no need to hold on to precise numbers or technical distinctions. Those details can fade gently. What remains is a sense of orientation. The universe is not a completed object surrounding us. It is a process we are embedded within. You are not standing beneath a finished sky. You're inside a space-time that is still stretching, still organizing itself, still revealing patterns that were set in motion long before any observer existed to notice them. And that process does not require attention to continue. It does not pause when we sleep. It does not resolve itself when we stop asking questions. It simply goes on, carrying galaxies apart, carrying light forward, carrying time with it. As you let these ideas settle, there is nothing left to solve here. No edge to reach, no final scale to measure. Just the quiet understanding that the universe you exist inside is larger than any single description, older in its complexity than intuition suggests, and still very much in motion. And somewhere within that motion, this moment passes too, gently, without needing to mark an ending.